Welcome, everyone. For today's prep, we're going to introduce the idea of surface integrals, and right now we're going to look at scalar functions. So let's get down to the main result here, and we're going to see how we actually calculate these. So we have a surface S, and we're going to start with the parameterization, a parameterization for that surface. So we're going to call our parameterization R, and it's in terms of two variables, u and v. We might use other variables, theta, things like that. And we have our x component, our y component, and our z component for this parameterization. So the thing we're going to be calculating is this surface integral of function f. So this is our surface integral. So it's the surface integral of this scalar function little f over the surface S. All right, so this is what we're calculating. Well, how do we calculate this? Well, we're actually going to calculate it using our parameterization. And we're going to convert this into just a standard double integral. And that's what we have here. So this surface integral is going to be equal to, we're going to use this other integral here for how to actually calculate this. So this is just a regular double integral over a planar region D. And D here is the domain for our variables u and v. All right. So again, we want to think of D here as it's a flat section of the xy plane or the uv plane here. And what our parameterization does is it takes that flat section of the plane and it kind of bends and distorts it so that we end up with a surface S sitting in three-dimensional space. And that's what the component functions give us. So what we're going to calculate here, this surface integral, there's a few things we have to do. We're going to plug the parameterization into our function. And then we also have to convert the differential. So when we have our function, wherever we see an x, y, or z, we're going to plug in the component functions that we have. And the differential here, ds, becomes this gadget that we looked at when we calculated the surface area for one of these parametric surfaces. So it's the partial RU, partial RV. We do their cross product, and then we calculate the length of this thing. So we have to convert the differential here, and it's that length of that cross product that helps us with the conversion. All right, so just before we get into this, what are some applications of quick applications for these surface integrals? So we're just going to list two of them. So first one, if the function we're integrating is a density function, so if we're integrating a density function, what this surface integral gives us, so let's say our function here was rho of x, y, z, so it's some density function. This would give us, not dA, ds. This would give us the mass. So if we integrate, if we're integrating a density function over our surface S, well then that integral, that surface integral, is giving us the mass of our surface. So if we have like a kind of a thin sheet of metal that's all bent and distorted, that's our surface, and we know what the density function is at any point along that surface. If we calculate the surface integral, we get the mass. Another application of this surface integral, and one we've already looked at without even really knowing it, is if f is equal to the constant function 1, well then this surface area gives us the, or spoiled it, the surface integral here gives us the surface area. So if we integrate the constant function 1 over this surface, we end up with the surface area. And actually, let's write out what we would end up with. So if we calculate it, we're going to convert this to a standard double integral. And if we convert our differential here, the ds is going to become this gadget here. So the length of RU cross RV dA. And that's just the surface area. All right, so we've actually seen a little bit of this when we looked at surface area. All right, so let's try an example here related to that one we looked at when we calculated the surface area for a sphere. So we're going to do the surface integral. The function we're integrating is x squared, and the surface here, S, is the unit sphere, x squared plus y squared plus z squared equal to 1. And we want to calculate this surface integral. So the first step, before we do anything, we got to get a parameterization for our surface. So we got to parameterize the surface. And the sphere here, this is one of our kind of our usual surfaces that we're going to consider. And so we go with our standard parameterization. So we kind of use our spherical coordinates as a guide. So the x parametric equation is going to be sine of phi cosine of theta. And our y equation is going to be sine of phi sine of theta. And our z equation is going to be cosine of phi. Now for spherical coordinates, normally there's a radius in front of all of these, but this is radius 1. So I'm just putting a 1 in front here. All right. So here are the parametric equations. And so phi and theta are the variables, the parameters we're going to be using. Well, what are the intervals for these parameters that give us one copy of the sphere? Well, phi, this tells us North Pole and South Pole, Northern Hemisphere, Southern Hemisphere. So we want the North Pole, which is phi of 0, and we want the South Pole, which is phi of pi, and we want everything in between. And then theta is Western Hemisphere, Eastern Hemisphere, everything in between. So we want 0 to 2 pi there. And then once we have this parameterization, then we want to work on, if we go back up, we want to work on calculating this cross product and the length of that cross product so we can convert our differential, just like if we were going to do surface area. And I'm going to reuse what we found in what we did in class. So we want to work on, and this takes a bit of work here, we want to calculate this RU cross RV. And what we found for the case of these spheres, for the case of a sphere, we found that this cross product, the length of this cross product, keep writing the wrong angle here, the length of this cross product was, what was it? It was the radius squared times sine of phi. So in class, we found that this was the radius squared times sine of phi. We used a whole bunch of trig identities to simplify it down. Now the radius here is 1. So this is just going to be sine of phi. There's a bit of work that went into this, especially trying to simplify it down. All right, so that's the first thing, is we want to get the parameterizer surface, then we work on calculating this gadget that helps us convert the differential, and then we want to start working on, setting up the integral. And the next step is going to be to actually convert the function that we're integrating. So let's plug in our parameterization R into the function we're integrating. All right, so let's see how this is going to look. And actually, let's start writing out the integral. So we're doing the surface integral, and the function we're integrating is x squared. And now we want to, right? Yeah, we're doing this surface integral. The function we're integrating is x squared. So in this function, wherever I see an x, I want to plug in my parametric equation. Wherever I see a y, I want to plug in my y equation. And wherever I see a z, I want to plug in my z equation. So in this case, I only have an x here to worry about. So I'm just going to replace that x with sine of phi and cosine theta. And then we have this squared. And while we're at it, let's also convert the differential. So this ds. And the ds here, so as we're writing this, this was our x squared that we replaced. And then the conversion for our differential is the length of that cross product for of our parameterization times dA, times the regular flat rectangular, or not necessarily rectangular, but our flat two-dimensional dA differential. So if we plug that in, we're going to have sine of phi dA. And again, that's because we've replaced the x squared with sine of phi cosine theta squared, and I've converted the differential now with that converting factor. And we're going to be integrating now not over region S. S is our surface, but we're going to be integrating now over the planar region D, the flat region D. And the flat region D is described by these inequalities. So now we're ready. Let's clean this up, and then we work on the integration. So we work on the integration here. So we set this up as an iterated integral. So how do we want to do this? Well, let's square this out and then consolidate all the phi terms. So we're going to end up with sine of phi cubed and cosine of theta squared. And when we do this, what is our phi limits going to be? 0 to pi. And our theta limits are going to be 0 to 2 pi. So when I convert this double integral differential dA, we're writing this as an iterated integral. I wrote my limits for theta on the inside, so my theta differential is going to come first, and then my phi theta comes last. And this is it. We have this written out now as an iterated integral, so now it just comes down to, what we're used to. So, and in this case, the limits of integration are constants, and our function that we're integrating here is factored very nicely for us. So we have the phi terms here, the theta terms here. So Fubini's theorem lets us split this up. So we can do our phi integration separate from our theta integration. And how are we doing? Okay. So, won't go through everything here. But for this sine cubed, how do we integrate this? Well, these are both trig functions. One of these trig integrals is an odd power. So when we have an odd power, the idea for integrating odd powers of trig functions here, is we peel off one of the powers. So in this case, it's sine that's odd. So we're going to peel off sine. So let's just kind of work on this one. So we're doing the integral from 0 to pi sine cubed. Let's do this one off to the side. All right, so when we have an odd power, the idea with an odd trig integral like this is we peel off one copy of our odd power and we put it next to our differential. Then all the other terms that are left, we want to convert these to the other trig function. So cosine. So kind of think of sine and cosine. They're kind of opposites of each other. So if we convert that sine squared into cosine, we can just use our usual sine squared plus cosine squared equal to 1. So we can write that as 1 minus cosine squared. And then from here we can do a u sub. So we let u equal cosine theta, and then the differential there, du, ends up becoming negative sine phi d phi. And so if we kind of plug in the pieces here, we end up with the integral from 0 to pi of 1 minus u squared. And then we have sine phi here. We have a negative sine phi here, so we're going to end up with another negative 1 here when we convert this into our u integration. And, while we're at it, I was going to leave the limits of integration in terms of phi, but let's convert them to u. So when I plug 0 into this equation, I get cosine of 0. Cosine of 0 is 1. So my lower bound is going to be not 0 anymore, but we'll use 1. And then when I plug pi in to cosine, I end up with negative 1. So my upper limit is going to be negative 1. And just to make this easy, rather than having this negative, I'm going to flip the limits of integration here. So that will integrate from negative 1 to 1. And then when we flip the limits of integration, the negative allows us to do that. So we end up with just 1 minus u squared. And from here, now this is just a nice, easy integral to do way back in Calc 1. And when we do that, what do we get? We end up with u minus 1/3 u cubed, evaluating from negative 1 to 1. And we end up with 1 minus 1/3. So we end up with 4/3. Right? Yeah, 4/3. So 2 minus 1/3 minus 1/3. So 4/3. All right, so that is our phi integral, and that's this one here. Just to get a little reminder on how we do trig integrals for odd powers. And now this other one, this is an even power, so that's where we use the half angle formula. So we won't go through that one. But what you should end up with here, we end up with a 4/3 from the first integral here, and we end up with pi when we do the second integral here. So just to remember our half angle identity, cosine squared theta is equal to 1/2 theta plus cosine 2 theta. So the idea is we use that half angle formula. It gets rid of the power, and then we can just not theta 1. That's once we integrate. Getting ahead of myself. So we use our half angle formula, 1/2 times 1 plus cosine of 2 theta. And then the idea is we get rid of the power, and then we have terms that we can integrate. So you should end up with, once you go through this, 4/3 times pi. All right, so we'll look at a special case. Next time in class, we'll look at a special case for when we're talking about the graph of a function. And then we'll see how to calculate the surface integral when our surface S has kind of multiple sides to it. and then we'll get into our vector fields, surface integrals for vector fields. So we'll see you then. Bye-bye.